Good afternoon.
I have to read a little bit earlier today, but I need to get my students now tomorrow.
All right, hello, kind people. How are we doing? I think I have two announcements for us. The first is that test number 6, the last test, is scheduled for Monday. I should hopefully get all the material by Friday, fingers crossed. Um, and then the other one is that there's one more in-class assignment. I sent out an announcement about it. I think it's due April 21st. And so, basically we're coming up to the end of the course. And the last right here, if you want to be excused from the final exam, you need to have an A in the class by next Friday, right? The cutoff right here, I think it's 11:59 Friday, because I have to look at the grades Saturday morning. And Saturday morning, I'll send out the exempt notices for those who do not have to take the exam because they have an A in the class. All right? Questions there?
And a lot of stuff be reopened,
A lot of what stuff?
like their recent works, not like more the older ones.
So send me an email for the assignments you want reopened. I can reopen the homeworks, but that's about it on WebAssign.
Okay.
That's so I can reopen those, but that's about it. Anybody else? All right. So let's going. So we were doing hypothesis testing. Earlier on, we looked at the basic concept of a hypothesis test. It's kind of like a jury trial where we're putting the null hypothesis on trial. But just like you need all 12 people to agree to convict somebody, you basically, out of 100 people, you need 95 of them to agree, basically, before you can convict the no, right? So you have to have 5% or lower threshold before we switch from the no to the alternative hypothesis, right? And in the p-value right here, we had to calculate the probability, again, that the null is true. It's really the probability of you getting that value given a specific null. So slightly different in terms of the language, but I like thinking about, hey, it's the probability that the null is true, and thus if I have less than a 5% chance that the null is true, that's when we switch over to the alternate hypothesis, right? I.e., we have to have strong evidence. And again, a reverse way of thinking about this right here is, hey, if the alternate hypothesis is true, then the null is not going to be true, right? And if it's not going to be true, then it's going to be really, really small chance that it's true. And that's another reason why they're not just saying, hey, 40-60 split, let's go with the alternate hypothesis. You want a really small probability that the null is true. All right, questions there? All right, so I skipped one small, so how you calculate your p-value? Again, you do this in SALT. So in SALT, you will put in the mean as 530. This means that it's going to be a right-tailed test. You put in your X bar right here as 560. So you put in your standard deviation as 116 divided by the square root of 100. And then you find the probability that X is greater than 562. Yes, that probability is going to give us our p-value. Questions there? So that takes us to the method that we skipped the last time, and that is the rejection region method. The key thing to keep in mind is that the rejection region method is exactly the p-value method. The idea is it doesn't matter which one you do, you get the same answer. And so I prefer just to teach the p-value method and hey, just use this method no matter what. But I still have to go over the rejection region method. So where is it? Oh, did I open the wrong one? I did, didn't I? Oh, but before I do that right here, I have to remind you of what's called a level of significance. Your alpha level is the cutoff value. Your alpha level is your cutoff value. So normally your alpha level is 5%, yes? Unless stated otherwise by the question. And again, the alpha level says, hey, if the probability is less than this amount, we are rejecting the null. All right, and so in other words, we're accepting the alternate hypothesis. Questions there? Notice right here, in this case right here, alpha in this case is 5%. Notice that they shaded 5% of the area right here, this alpha level right here. This shaded region is called the critical region. And quite simply, when you run and you get your data, if your data scores fall within the critical region, then you reject the null. If your data score fall outside of the critical region, then you fail to reject the null. That's the basic way that your rejection region method works. And let's go ahead and do that, shall we? 1, 2, 3. So let's go ahead and look at the rejection region method right here. So level of significance right here. Critical. I just explained all of this right here. Again, if alpha is 5%, it means that the critical region right here will cover 5% of the data. If your value of your test statistic is inside the critical region, then we reject the null hypothesis. And that's the rejection value method. Why did they not have a title saying all right, so I'll draw it out then, because they didn't do a very good job of explaining it right here. So the section right here I'm looking for is the rejection region method. And quite simply, the rejection region method says you first pick a value for alpha. Generally, that's 5%, 0.05. Okay? Once you picked that value for alpha, you create your normal distribution and you find out the probability of alpha, i.e., you shade the region. And again, the shading is going to be based upon the type of test you have. In this example, it is a right-tailed test. Yes? I'm shading the right tail. If it was less than, it will be a left-tailed test. Yes? But in this case right here, it's a right-tailed test. What you then do is calculate your test statistic. And again, I'll show you how to calculate this again in SALT, but your test statistic is simply equals to the score minus the mean divided by the standard error, which is going to be sigma divided by the square root of n. And it goes simply like this. If your score, your test statistics falls within the rejection region, then you will reject the null. So this is called the rejection region. So if, for example, you get a test statistic of, say, 2.7, and 2.7 happens to be right here, 2.7, that means we'll reject the null. But let's say we get a test statistic of 0.5, 0.5 is down here, test statistic, then we will not reject the null. If you're in this huge area over here, we fail to reject the null. Again, notice that this region over here is huge, right? That's representing the 95%. Yeah? Yes, that's representing the 95%. So there's a 95% chance, hey, we're sticking the null. There's a 5% chance on this side right here, we're going to reject the null. Questions there? Okay. Yeah, when I do the next example, I'll show you how to calculate the test statistic. But the key thing right here, the test statistic is simply your z-score. You guys remember how to calculate the z-score? You plug the numbers in and the value at the bottom and solve your z-score? Yes? That's how you calculate your test statistic. You just remember it's a z-score, you'll get it right each time. Questions there? All right. So let's go ahead and solve one of these using the rejection region method. Where is my example that I wanted to work? I can see how they prefer the p-value, just like me. All right, so let's work this one right here. So again, this was the story about the taller people being smarter, right? The CEOs are taller, so they're smarter. And we did this one last time. And you see right here, z equals x minus mu over sigma n. This right here, this is your test statistic of 0.67. So let's go ahead and put all of this information in. Alpha is 0.05. Let's go ahead and put all of this information in, and let's go ahead and see if we can figure out whether or not to reject or fail to reject the null. All right? So where's my good friend, Mr. Saltz? Mr. Saltz, Mr. Saltz, where are you? Oh, there he is. Hi. So again, first things first, we select a normal distribution. We put in the mean and the standard deviation. The mean was 69.7, and the standard deviation, is the standard deviation 3? No, I have to divide it by the square root of n, so the square root of 100, so the standard deviation is 0.3. Yes? So put in here 69.7, and my standard deviation is 0.3, right? A left tail test. Oh, sorry, right tail test. And now here's the difference between this method and the p-value method. In this method, in the box, you put the alpha level. In your probability box, you put the alpha level. In this example right here, it's going to be 5%. And so when I put that 5% in right here, you can see right here, it's shaded right here in this region right here. All right? This is my rejection region. If my test statistic is inside this region, I reject the null. If the test statistic is anywhere else, way over here, I fail to reject the null. All right? Questions there? Now they calculated the test statistic for us. The test statistic was 0.67. And so if I come back over here, too fast, I guess. If I come back over here, 0.67. This is 0, this is 1. 0.67 is right here, yes? And so therefore, my test statistic is right here. Is this in the rejection region? No, and because of this, we will fail to reject the null. All right? Questions there? And that's how the process works. You put the alpha level instead. The alpha level is my cutoff right here. And then you find the test statistic and you figure out if the test statistic is in the shaded region, reject the null. Not in the shaded region, fail to reject the null. Questions there? All right. One last thing to show you right here, how you calculate the test statistic. Remember, the test statistic is your z-score. You have to put in the score. I believe it was 69.7. 69. No, 69.9, sorry. You put that score in right here, and then this right here will give you your z-score. So you put in the evidence, 69, that's the height of the CEOs, and then this will give us our z-score 0.67. Questions there? All right, cool. All right, I think that's all of it for the whole section. Yeah, this is using a TI-85. We don't need to do that. Oh, this one last thing right here. There's a relationship between a hypothesis test and a confidence interval. If you have the mean of 74 and then you have your alpha of 0.05, right? If you create a confidence interval about that mean, if this confidence interval contains your score, what was your score again? Contains your score of 80, then that will tell you that this mean is true. If it does not, did we do this example? Oh, we started, but we didn't finish it. So let's go ahead and run this example. In a large company, the attitude of workers are regularly measured with standardized tests. The score on the test range from 0 to 100, with high scores indicating a greater satisfaction with their job. The mean score overall for the company's employees is 74, with a standard deviation of 8. Some time ago, the company adopted a policy of telecommuting. Under this policy, workers should spend 1 day per week working from home. After the policy has been in place for some time, a random sample of 80 workers was given the test to see whether their mean level of satisfaction had changed since the policy was put into effect. The sample mean was 76. Assume the standard deviation is still 8%. Can we conclude that the mean level of satisfaction is different since the policy changed? Again, at the 05 level, alpha level, 05 level. All right, that was a lot. Can anybody tell me what the null and alternative hypothesis for this question is? All right, let me give you a hint. Let me give you a hint. Let me give you a hint right here. The company, over time, the mean score was 74, yeah? With a standard deviation of 8. The company then put in a new policy of telecommuting, and then the score went up to 76. Right? How many workers did they sample? 80 workers. All right, so I kind of underline all the numbers in here. What's the null and alternative hypotheses for this right here? Oh, one last thing. It says that the satisfaction different since the policy changed? What's the null and alternative hypothesis right here? The null will be mu equals 74. Remember, the null is the long run history. It's the thing that was before we made the change, right? It used to be 74. We then instituted a new policy, right? Now, what's the alternate hypothesis going to be? It's going to be not equal. All right? Why are you not waving back? What's wrong with you? The mean is going to be not equal. The reason why it's a not equal right here, because it didn't say less than, right? They didn't say the score is less than. They didn't say greater than, they said different, right? Difference two means not equal. So that's your null and that's your alternate hypothesis. Again, remember the null is always equal. Question third. This is going to be a two-sided test. All right, question third. All right, so it's a two-tailed test. All right, so calculate the test statistic. So let's calculate the test statistic in SALT and then come back and calculate it over here. Excuse me. Ah, So I gotta go into, where's my good friend SALT? Where's my good friend SALT? So I'm over here in SALT. The mean was 74. What was the standard deviation? Not 8. 8 divided by the square root of 80. So it's a calculator, so I'm gonna have to calculate the actual score. Oh, where is my calculator when I need it? And so it's going to be 8 divided by radical 80. And that's a decimal of 0.8944. So we'll take that, 0.8944. And so that's going to be our standard deviation. Questions there? Again, you can see how you can fall for, oh, the standard deviation. Instead it was 8, right? If you have this one number off, it throws all the other things off. And then over here, we're going to have a two-tailed test right here. Okay, questions there?
Why is it two-tailed?
Because it's different. It's not less than, it was not greater than right here, is because of, sorry. The null hypothesis right here. See how it's different right here? That gives you a two-tailed test. If it was greater than, it'd be right. And so forth and so on. All right, questions there? Oh, so I'm doing my two-tailed test. All right, so now this part right here, again, is a little bit tricky when you want to do this in SALT right here. Because you see right here, there are two numbers that we need to plug in right here. Yes? What score did they get? I guess you see, I got you a little bit of runaway advantage here. What score did they get on the survey? Yes.
76.
76 was the new average, yes? But is 76 right here higher than 74 or less than 74? So you're gonna have to put it on the higher side. If it was smaller, we would put it on the smaller side. So it's gonna put it right here, 76 right here. And so you see the score right here, 2, 2, 3, 6, 1. You put it over here, but the negative version. Because it's a two-tailed test, it has to be the same amount on each side. Again, this is slightly different than from your regular one-tailed test. And then you'll see right here, 76 and 72. 76 is 2 points above 74. 72 is 2 points below 74. All right? Again, the key thing right here is these two z-scores must be the same. Questions there? Now with this, you can see right here, this is going to be our p-value of 0.25, 0.025, or 2.5%. Yes? So given that you know the alpha level is 5%, do we reject the null or do we fail to reject the null? Let me write it down for you. Might be easier if you can see. So again, this is it right here. The alpha level is equal to 0.05. That's what the question said, yes? And then the p-value is 0.025. Do we reject the null or do we fail to reject the null? Which one is fail, which one is not fail to reject? Which one? You're doing this. Which one? All right, let me give you a hint. There is a 2.5% chance, 2.5% chance that the null is true. There is a 2.5% chance that the null is true. Should I stick with the null? No, it doesn't make sense, right? It's if I say it was 0.1%, would you stick with the null? No, right? This number right here, you see the 5% number? That's my cutoff value. I would take 10%. I would take 50%. The null has 80% chance. I would select the null, yes? 5% is my cutoff. If I am less than 5%, I reject the null. And so we are going to reject the null. So in other words, we are going to accept H1. We are going to accept the alternate hypothesis for this question. Questions there? Comments? Queries? Concern? And so basically the alternate hypothesis is yes, the survey score is different from before. So in other words, the telecommuting has made a difference in satisfaction for our work. Questions there? Comment? Queries? Concern? All right, so that's what they have for us right here. So again, you get your two areas. When you add them together, you get 0.025%, and 0.025 is less than 5%, and so we have to reject the null hypothesis. Last name. You okay?
Yeah.
Okay. So since the p-value is less than the alpha level, we reject the null. So in other words, for conclusion, we're going to say there is evidence to conclude that the mean score among employees has changed because of the adoption of telecommuting. Questions there? Comments? Queries? Concerns? I can see you guys forgot a little bit back from Friday to now. Forgot a little bit from Friday to now. All right. Questions? We already did this part already. Oh. All right. So did I do this part already? No. So basically what they're trying to say right here is if we were to construct a confidence interval right here for the mean score around 74, you notice right here that the score that they got is not within the score that they got is not within this is not within the score right here. This another way to express this information about mu is through a confidence interval. If we construct a 95% confidence interval for the mean about the score, so again, remember the score we got was 76. Yes, that was the score. They created a confidence interval. They added 1.75, and then they subtracted 1.75 right here. They got these two scores right here. Notice that the number 74, which was the old mean, is not inside this region right here. Right? The 74, the old mean is not inside. And so this is saying, hey, we need to reject the old mean. It's not inside the confidence interval. So therefore the old mean cannot be correct. Questions there? You guys remember how to construct the confidence interval? At least remember how to do online, type the button thing, you need 4 numbers to construct a confidence interval. Y'all better hope y'all did well on all them tests. You gotta do it again on final exam. All right, so that takes us into 8.2. The other two chapters are shorter because they don't have to re-explain everything. Just gotta show you how to do them. All right, so 8.2, again, testing, but this time we're doing the testing when sigma is unknown. When sigma is unknown, the only change is we're switching back to the student T's distribution. Yes, that's the only difference right here. We're switching back to the student T's distribution. Again, the same 4 principles apply right here. Again, sigma is unknown. In 8.1, sigma was known. Use a simple random sample, and then the population size. Normally, you need larger than 30 or more, except if the underlying population is already normal, then any size will do. Yes, we need one of those two things for the central limit theorem to hold. You guys remember the central limit theorem? Yes, you have a big enough size population, it becomes normal. Yes, the average, the mean, the distribution of the means become normal. Whew, y'all looking at me like, whew, I gotta go back and study that. All right, here we go. Suppose that in a recent, there's my plate button. Suppose that in a recent medical study, 76 students were placed on a low-fat diet. After 12 months, their sample mean weight loss was 2.2 kilograms with a sample standard deviation of 6.1 kilograms. Can we conclude that the mean weight loss is greater than 0 at the 0.5 level? And right, if you're doing a medical study with 7 subjects, most likely sigma is not known, correct? Because sigma is not known right here, we cannot use the z-test, so we have to use the student t-test, yes? And so we have the one key thing right here, 76 is greater than 30, and sigma is unknown, and so we're going to be using your t-test right here. Questions? All right, and so let's go ahead and set this up right here. Really, we've gone through this last time already, understanding t. Guys, remember how to calculate the number of degrees of freedom? There were 76 people in the study, so what's the degrees of freedom? 75. Good. And so now they want us to perform the hypothesis test. Again, let me underline some things for you. How many people were in the study? 76 right here. They want a mean weight loss that is greater than 0. The alpha level is 0.5, and your standard deviation is 6.1, and your sample mean is 2.2. So with all of that, what is the null and alternate hypothesis? Going once, I'm about to tell you. The null is equal to 0, and the alternate hypothesis is going to be greater than 0. Yes? Right? Again, because the idea right here is they want to conclude that the mean loss is greater than 0. Right? And so your null hypothesis is 0, and your alternate hypothesis is that we are greater than 0. Again, if the alternate hypothesis is true, it means that diet is causing people to lose weight. All right? If the alternate hypothesis is true. This is a right-tailed test. All right, calculate the test statistic. Again, I don't think we're going to need to do it by hand, but the answer right here is 3.144. Again, we'll show you how to calculate all of these in 1 second. And your degrees of freedom is n minus 175. All right, let's roll. Are you ready? Let's show you how to do this in SALT. So, there we go. Heading to SALT. And again, we head back over to inferential statistics. Once we get here, right here, again, we select one sample T. We put in the sample mean. It was 2.2, correct? We put in the sample standard deviation. It was 6.1, correct? 6.1. And again, notice they don't ask for degrees of freedom. They ask for the sample size. So you put in right here, 76. Questions so far? Just like with the confidence interval, you're going to need 4 numbers to do a hypothesis test. We need 1 more, and that number is going to be your hypothesized mean. And so it's kind of written down a little bit weirdly, because normally we're accustomed to seeing mu is greater than, and so they have it backwards for some reason. But you look for the word And so it says greater than right here. So remember the alternate hypothesis was that mu was greater than 0. It's kind of backwards, right? That's something I would just look for the word greater than. All right? Questions? And all you do is hit generate results and it will run the test for you. So I hit the generate results right here. It ran the test. Double check that your null and your alternate hypotheses are correct. Because if they're not, then it's going to throw the whole thing off. And then all you need is the p-value, which is 0.00. Let me say that's really small. 0.001194. That's 0.1%. Move the decimal point twice. Right? Move the decimal point twice. Yeah, 0.001%. And so, do we reject the null or do we fail to reject the null? Don't you all raise your hand at the same time? All right, so I've given everybody a chance to make up their mind. So, all those in favor, you reject the null, raise your hand. All right. All those in favor of you fail to reject the null, raise your hand. Do you remember what the alpha level is? What's the cutoff value? It's 5%, yes? Did you and the p-value is that smaller than or is that bigger than 5%? If it's smaller, we have to reject the null. And so we do reject the null in this example. Questions there? Questions there? We do reject the null in this example. But any questions about running the hypothesis test? You need 4 numbers. Sample mean, sample standard deviation, sample size, and then the mu value. Questions there? You're going to have a hard time trying to figure out, do I reject the null? All right. And so, again, your test statistic, it shows your test statistic as well. It's right here, 3.144 right here. It shows your test statistic. You get your p-value. Again, look at this. Look how small this p-value is. Look how small the area they have to shade is right here. Right? All of this right here. And so the decision is we are going to reject the null hypothesis. There is a 0.1% chance that the null is true. Why are we sticking the null, y'all? And so our conclusion is that, yes, this diet will help you lose weight if you had adhered to it for a 12-month period. Question there. You should underline the word adhere because that's the real issue with most diets. Not they work or not. It's that you can pick on them. Questions there? Oh, cool. All right, so again, they just show you how to do it on the TI 83/84/85/97 plus. But like I said, we don't require that you use this calculator. But again, right here, notice right here, mu is greater than 0. You are putting the 4 numbers you need, and it gives you both your test statistic and your p-value. Again, we just did this right here. Inferential statistics, plug those numbers in. Again, make sure it's a 1 sample T. And then, remember in the previous chapter, we clicked confidence interval. And this one, we're using the hypothesis test. And then those are your results. Always double check your null and your alternate hypotheses, right? That makes a huge difference. If you switch the sign, the p-value is going to switch sides. It's going to go up to like 99.8918%. It's going to switch sides. So you have to have the right sign. And then, other than that, see your degrees of freedom, double check that. Either one of these, because again, if you enter the wrong number, it's going to skew the result. Questions there? Cool. Again, it might be helpful if you write the alpha level down so you can see 0.05. Again, this number is less than, right? smaller than my cutoff value, and so I should reject the null. Questions there? You can raise them. You raise your hand slowly if you want to. That's fine. Like you just wave in the air, like you just don't care. No. Y'all still afraid of talking in class? All them years you've been going to school, y'all haven't been practicing. No. Ugh, 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 I tell you. All right, and like I said, the 8.2 was not going to be long because they don't have to re-explain the concept, right? The hypothesis test. This is how to show you how to run the test. And then in 8.3, again, 8.3 is not long either. Well, they claim they have another slideshow. Let's find out. But shut up. Miss anything. Oh, I know what it is. Another example. All right, so let's do this example. I do apologize again. These examples are notorious for the long length and the problems. Again, students just love word problems. The generic drugs are low-cost substitutes for brand name drugs. Before a generic drug can be sold in the United States, it must be tested and found to perform equivalently to the brand name product. The US FDA is now supervising the testing of a new generic antifungal ointment. The brand name ointment is known to deliver a mean of 35 micrograms of active ingredient to each square centimeter of skin that is approximately normal. As part of the testing, 7 subjects applied the ointment. 6 hours later, the amount of drug that has been absorbed into the skin is measured. The amounts in micrograms are 2.6, 3.2, 2.1, 3.0, 3.1, 2.9, and 3.7. How strong is the evidence that the mean amount absorbed differs from 3.5? Use the alpha level, again, because we're in the science region right here. Notice the alpha level is much smaller. Use the alpha level of 0.01. Everybody understand the question? So, okay, we're doing a hypothesis test, yes? All right, so do we use the z-test or we use the t-test in this example right here? Let me help you then. What is sigma? The standard deviation. What is sigma? No, sigma. The mean is the mean. Sigma is standard deviation. What is sigma for this problem? Standard deviation, the population standard deviation. It is unknown, yes? This is a new drug that has just been created. Remember, sigma, the population standard deviation, is the number that's always been there. We've been making these drugs for 500 years. We know what's the standard deviation. This is brand new, so it does not exist, right? Right? And also, the underlying population is approximately normal. And so that's what we need. Sigma is unknown. And so because of that right here, that's enough for us to do the t-test right here. Question? All right, so we got to perform this hypothesis test. Can anybody tell me what the null and alternate hypothesis is going to be? Yes, you're both correct. Mu is equal to 3.5 HO and then not equal to 3.5 H1. Null and alternate hypothesis. Questions there? All right, cool, cool, cool. This is going to be a two-tailed test. Woohoo! 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 All right, again, we don't expect you to go ahead and to do all of this by hand. You put all of this into a CSV file and upload it into Salt, and Salt will do all the calculations for you. Yes? Okay. Okay. Oh, cool. But they did for us right here. And so we get your So you get your standard deviation as 0.4995, and you get your mean as 2.94. All right. So the average of the 7 numbers was 2.94, and the standard deviation for the 7 numbers was 0.4995. Questions there? You can do it by hand. It's only 7 numbers, right? The average, add them all up and divide by 7, yes? You could do them all by hand, but why? Why? And then remember, we need 4 numbers to do a hypothesis test. Anybody remembers what those 4 numbers are? We need 4 numbers to do a hypothesis test. What are those 4 numbers? You don't want to hint? The mean, standard deviation. That's the mean. The sample size, not degrees of freedom. And the last one right here is the null hypothesis. Remember, mean equals 3.5. So you need that 3.5 as well. All right. Questions there? So in other words, we're going to put these last 3 numbers in, 1, 2, 3, and we're going to put the 3.5 in there. Questions there? Questions in there? All right, so let's go ahead and run the test. So where is my good buddy? Stop. There we go. I didn't forget already. What was the sample mean? 2.94. You guys not paying attention either, huh? The sample mean is 2.94. See right here? X bar, 2.94. The sample mean is 2.94. The standard deviation was 0. What was my standard deviation? My standard deviation was 0.4995. 4995. And then there were 7 people in the study. Okay. What's the hypothetical mean? What's hypothesized mean? 3.5. And then this is going to be, what kind of test is it? 1-tailed or 2-tailed test? 2-tailed test is going to be not equal to. Sorry, 3.5. There we go. Questions? Then all I have to do is generate the results right here. And then I just got to read this right here. Again, always double check your null and alternative hypothesis. Mu is 3.5. Mu is not 3.5. There were 7 people in the study. And you can see right here, this right here is my p-value. Do you guys remember what the alpha level was? 0.01. Remember, this was a science question. For the science, I want the alpha level tends to be even lower. So the alpha level is 0.01. All right. So, question. Given the alpha level is 0.01, do we reject the null or do we fail to reject the null? All right. All right. So raise your hand. All those in favor of you rejects the null. All those in favor of you fail to reject the null. We still divided, y'all? We still divided, y'all? All right, let me write it down again. Maybe it helps if you can see it. Let me help if you can see it right here. The alpha level is 0.01 and the p-value is 0.025. Do you reject the null or do you fail to reject the null? Is the p-value smaller than the alpha level? Is it smaller? It is not, correct? 0.1, 0.2. This is the smaller value. Therefore, you fail to reject the null. We gotta pray about it. We gonna pray about it? Are we okay? Question? But we're still not okay. Don't have no question. How can I get you guys to remember this? How can I get you guys to remember this? How can I, yes. Remember, the alpha level in this example is not 5%. The alpha level in this example is 1%. They changed it. Normally it's 5%. But in this example, they changed it to 1%. Right? Normally in the sciences, the alpha level is lower. All right? Is that what's throwing you off? The 5%, you're thinking 5%, and the 2% is small, is that what's throwing you off? Right? You have to know the alpha level. You have to set the alpha level before you run the experiment. Because if not, you can just change it to make the experiment pass. Yeah? And so you have to know the alpha level before you start.
So if we find the p-value and it's larger than the
Yeah.
alpha value, then that's what we reject.
No, smaller to reject.
Okay.
Smaller to reject. That's right. The p-value needs to be smaller than the alpha level. Then you reject. All right? People in the back, in the back, in the back. Do we need to make like a flashcard or something? Again, the key is the p-value must be smaller to reject. Is 0.25 smaller than 0.01? It's not smaller, is it? And so we fail to reject.
So that would be acceptable.
We never say we accept the no.
Okay, so we have to use fail to reject.
Yes. Okay, we accept the alternative, but we never accept the no. Again, think about it. They're literally saying there's a 0.25% chance saying the null is true. We can't say the null is true, right? All we can say is there's not enough evidence to reject it. So we say we fail to reject it. Anybody else? Anybody else? You want me to say this, but say, you want me to say it, but say it in English? Say it again, but this time in English? All right, all right. All right, and so the p-value is greater than the alpha level, and so we fail to reject the null hypothesis, again, at the O1 level. So in conclusion, there is insufficient evidence to conclude that the mean amount of drug absorbed differs from the 0.305. Again, so it says they may be equal, but they can't guarantee. They're not saying we're accepting the null. We're just saying we can't say they're different. All right? Questions there? Okay. I just showed you guys how to plug all of this into SALT. Again, you need 4 numbers. You need the sample mean, the sample standard deviation, the sample size, and then you need to know the hypothetical mean, 3.5. And of course, you guys choose what kind of alternate you have. In this case, it was a 2-tailed test. And so we chose not equal to. Questions there? All right, I am out of time. But that is the end of 8.2. Yeah, this is another, well, I guess I can do the other example if I move on to 8.3. But let's take attendance. Oh, what? How is things I got open? What's this?
Just like, I'm not really reading for it. Okay.